Okay, so now we're moving on to trig identities. So we're going to go pretty quickly through this lesson because there's a lot of kind of basics that we're not going to go over. But basically what an identity is it's something that we know to be true. So the one example they give here, is that no matter what x is, x plus 1 squared is equal to x squared plus 2x plus 1. That is an identity because it is independent of what x is. An equation is something like up here, where we have 2x squared plus 3 equals 11. That is an equation because it is only true for certain values. So an identity is true for all values of x. X plus 1 squared must equal x squared plus 2x plus 1. So all of these, basically everything on our formula sheet is essentially an identity. The basic ones here, we know that's always true. If we're looking in our unit circle, sine theta is always equal to y over r, which is the opposite in the hypotenuse. We have our reciprocal identities. Also, these are on our formula sheet. Cosecant x is equal to 1 over sine. It's also just the definition of cosecant x, but we call it an identity because those two are always true no matter what x is. So we have two things we need to do with identities. We need to verify them and we need to prove them. So verifying identities is where we can substitute in a value and we can just check that left-hand side equals right-hand side for that angle or that value of x. This does not prove anything. It only shows that it works for that one value we tested. So for example, verify the following identities for the value given. So we want to double check that tan of x equals sine x over cos x when x is 60 degrees. So we're going to calculate tan of 60 degrees. And if you use the hand trick or the unit circle or even your calculator and use this in a decimal form, that's fine too. But you'll get tan of 60 as root 3. The right-hand side, so we're going to substitute in 60 here. We're going to have sine 60 over cos 60. Well, this also equals root 3. So we have, since both of these sides are equal, we have verified that this statement is true for x equals 60 degrees. We haven't proven it to be always true. We've just shown that in this case it is true. So we can do the same thing here with pi over 6. So remember that when they put the little squared sign here, it really means we're squaring tan of pi over 6. It's not squaring pi over 6. It's squaring the tan of pi over 6 plus 1. And again, you can work in exact values here if you want. And you get root 3 over 3 and squared, but you can also just punch this into your calculator, and it's obvious that if the two decimals are equal or not. Well, root 3 over 3 squared is the same as 1/3. 1/3 plus 1 is 4/3. So we got the left-hand sides equal 4/3. What happens to the right-hand side? Well, remember secant squared is 1 over cos squared. And this gives us 1 over root 3 over 2, all squared, which does give us 4/3. So, 4/3. So right-hand side equals left-hand side. We've verified this identity for pi over 6. Again, we haven't proven that it's true, but we have verified it. We're going to skip examples 2 and 3. They're very basic, and I find it actually is more confusing to go over them than if we just trust those very basic ones to be true. So, because I think we've already talked about that when we built our unit circle. So, a few identities we have here. Tan of x equals sine x over cos x. Cotan equals cos x over sine x. And what we call our Pythagorean identities, sine squared x plus cos squared x equals 1. And 1 plus tan squared x equals secant squared x. And 1 plus cotan squared x equals cosecant squared x. These all come from using the Pythagorean theorem on our special triangles or unit circle. What's important to remember is that these can all be rearranged. So sometimes it's not quite as obvious when we need to use them because it's written in a different form. So this one here can be written, if we first subtract cos over, we get this version. We subtract sine squared x over, we get this version. But it's really all the same relationship. They've just been manipulated. So the same thing goes for this one. Can be rearranged to look like this. This one can be rearranged to look like this. So you need to be prepared to kind of recognize things in different forms, because sometimes we'll be looking for something like this and we can replace it with 1. Other times we'll see that we have sine squared x and we need to replace it with this, or vice versa. So you do need to know that these can be rearranged. Some people like to kind of write some of the most common rearrangements on their formula sheet when they sit down at their test. So let's do some examples. Express each as a single trigonometric ratio. Use a graphing calculator to verify. So one of the biggest things you're going to find when you're working with these is you need to remember how to make common denominators. So in order for me to add these two things together or to start changing anything, there's nothing on my formula sheet that says sine squared x over cos squared x. Or is there? Sine squared x over cos squared x would be tan squared x, so I guess you could technically use that ratio if you wanted, but we're going to go through it the long way here. So sine squared x over cos squared x plus 1. So in order to add it to something, I need to make a common denominator here. So in order to do that, I need to multiply top and bottom of that fraction 1, which is really 1 over 1, by cos squared. So now I have sine squared x plus cos squared x all over my denominator of cos squared x. So I always say this is when you do a happy dance if you see sine squared x plus cos squared x, because now I can get rid of all of that and just make it a 1. Well, 1 over cos squared x is the same as secant squared x. So again, I think you could have written this as tan squared x plus 1. We know that 1 plus tan squared x is secant squared x is actually a rearrangement of something on your formula sheet. So that one I guess we could have done in 2 ways. Here we have, and to verify using a graphing calculator, what you would do is you would graph this in F1, and you would graph this and F2, and you just want to make sure those graphs overlap everywhere. If you get the same graphs, then you have double checked on your graphing calculator that these two are really the same thing. B, sine x plus cotan x over times cos x. So one of the things that usually works for us is if we start by rewriting everything in terms of sine and cosine. So cotan we can write as cos x over sine x. Okay, well now I can simplify this to be sine x plus cos squared x over sine x. Now again, I somehow need to bring these together. So I need to make a common denominator. Right now there's really a denominator of 1. So I can multiply top and bottom by sine x. This gives me sine squared x plus cos squared x over sine x. Well, again, we have sine x plus cos x squared x is 1. So this is 1 over sine of x, which is the same as cosecant x. So again, to verify it by graphing, graph the original in F1, graph 1 over sine x in F2, and make sure the graphs are the same. Next example, express 2 tan A in terms of sine A and cos A and write in simplest form. So 1 plus tan squared A, 2 tan A over 1 plus tan squared A in terms of sine A and cos A and write in simplest form. So I'm going to start by just writing everything in terms of sine and cosine. Now it's tempting to start canceling things out here, but we cannot cancel things out when we have an addition sign here. So I'm going to make a common denominator on the right-hand side, or on the bottom, with this 1 on the right-hand side, so that I can add these together. So I need a denominator of cos squared A. So I'm going to multiply by cos squared A on the top and the bottom. So now my denominator is cos squared A plus sine squared A over cos squared A. Well, we know that this is equal to 1. So 2 sine A over cos A. To divide by 1 over cos A is the same as multiplying by cos squared A over 1. Right, so here I was dividing by 1 over cos squared A. That's the same as multiplying by the reciprocal. So now this cos A cancels out with one of the cos A's I have on top. So I can write it like this. Now there is an identity on your formula sheet. You could actually write this, I think it could be sine of 2A. That would be fine too. This is how they happen to leave it here. 6. Factor the following trigonometric expressions. So this is a little bit more complicated factoring than we did when we were solving equations. But we can still start by taking out the common factor of 3. Now this is a difference of squares. So it gives me this. This one is actually a difference of squares again. So I have that. And I can rewrite this. But this factor right here is cos theta squared plus sine theta squared. This is just equal to 1. So that means my factored form of this is really 3 cos theta minus sine theta times cos theta plus sine theta. So this last factor is just equal to 1, so we don't need it there anymore. So sometimes it just tidies up a bit nicer. Here I can factor out a sine squared theta. And now if you look on your formula sheet, 1 plus cotan squared theta is actually cosecant squared theta. Well, cosecant squared theta is really 1 over sine squared. So all of this really just equals to 1.